Lesson: Selecting appropriate machine learning models. Selecting the appropriate machine learning model is a crucial step in the AI model development lifecycle, as it directly impacts the performance, efficiency, and success of the AI system. The process of model selection involves evaluating various algorithms, understanding the nature of the data, and considering the specific requirements of the task at hand. This lesson will provide actionable insights, practical tools, and frameworks that professionals can implement to effectively select and optimize machine learning models for diverse applications. The first step in selecting an appropriate machine learning model is to understand the problem type and data characteristics. Machine learning problems can generally be categorized into supervised, unsupervised, and reinforcement learning. Supervised learning deals with labeled data and is further divided into classification and regression tasks. For classification, models such as logistic regression, decision trees, support vector machines, and neural networks are commonly used. For regression tasks, linear regression, ridge regression, and regression trees are popular choices. Unsupervised learning, which deals with unlabeled data, often involves clustering algorithms like k-means or hierarchical clustering, and dimensionality reduction techniques such as principal-component analysis. Reinforcement learning is used when an agent needs to take actions in an environment to maximize cumulative rewards, with algorithms like Q-learning and deep reinforcement learning. Once the problem type is identified, it is essential to understand the data. The size, dimensionality, and quality of the dataset can significantly influence model selection. For instance, if the dataset is small, simple models like linear regression or decision trees are preferable due to their lower risk of overfitting. Conversely, large datasets can benefit from more complex models like deep neural networks, which can capture intricate patterns in the data. Furthermore, the presence of noise and outliers in the data can affect model performance. Techniques like data preprocessing, feature engineering, and normalization are crucial in preparing the data for model training. Practical tools and frameworks play a vital role in facilitating model selection and evaluation. Scikit-learn, a popular Python library, offers an extensive range of algorithms and tools for model selection and hyperparameter tuning. By leveraging Scikit-learn's grid search CV and randomized search CV, professionals can efficiently explore various hyperparameters and select the best model configuration based on cross-validation results. Additionally, TensorFlow and PyTorch are powerful frameworks for building and training deep learning models, providing flexibility and efficiency in handling complex tasks. A crucial aspect of model selection is the evaluation and comparison of different models. This involves splitting the data into training and testing sets, training multiple models, and assessing their performance using appropriate metrics. For classification tasks, common metrics include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve. For regression tasks, metrics such as mean squared error, mean absolute error, and R-squared are typically used. It is important to select metrics that align with the business objectives and the specific nuances of the problem. Real-world challenges often involve trade-offs between model complexity, interpretability, and computational efficiency. For example, while deep neural networks can achieve high accuracy, they are often considered black box models, making it difficult to interpret their predictions. In contrast, decision trees and linear models offer greater interpretability but may not capture complex patterns. Professionals should carefully consider these trade-offs and select models that balance accuracy with the need for transparency and explanation, especially in regulated industries such as healthcare and finance. Case studies provide valuable insights into the practical application of model selection techniques. For instance, in a study on credit scoring, researchers compared several machine learning models, including logistic regression, decision trees, and random forests, to predict default risk. The random forest model outperformed others in terms of accuracy and interpretability, enabling the financial institution to make informed lending decisions while maintaining regulatory compliance. This example highlights the importance of empirical evaluation and domain-specific considerations in model selection. Furthermore, the deployment environment and computational resources should be taken into account during model selection. Edge devices or environments with limited processing power may require lightweight models that can run efficiently with minimal resources. On the other hand, cloud-based applications with access to powerful computing infrastructure can leverage more complex models, such as deep learning architectures, to achieve superior performance. Professionals should also consider the potential for model drift and the need for continuous monitoring and retraining. In dynamic environments where data distributions can change over time, models may become less effective. Implementing automated monitoring systems to detect performance degradation and trigger retraining processes is essential for maintaining model accuracy and reliability. Lastly, ethical considerations and bias mitigation are integral to responsible AI model development. Bias in training data can lead to unfair or discriminatory predictions, posing significant risks to individuals and organizations. Techniques such as fairness-aware learning, adversarial debiasing, and data augmentation can help address bias and ensure equitable outcomes. Professionals should prioritize transparency, fairness, and accountability throughout the model selection and deployment process. In conclusion, selecting an appropriate machine learning model is a multifaceted process that requires careful consideration of problem characteristics, data properties, model performance, and real-world constraints. By leveraging practical tools and frameworks, professionals can efficiently evaluate and optimize models to meet specific business objectives. Continual monitoring, ethical considerations, and adaptability are vital components of a successful AI model development strategy. Through empirical evaluation, case studies, and a deep understanding of domain-specific requirements, professionals can enhance their proficiency and deliver robust, reliable, and responsible AI solutions.